for first, second, and third, and then in top 10, you get plus 20. Along with that, we'll feature your name on the Kid Teach Good website, and you may or may not get cool merch. We don't know about that yet because of COVID. Okay, any questions so far? This is number sense for people asking. Okay. So we're going to start with sequences of series. If we have time, we'll move on to prime factorizations. And then if we have time after that, we'll go into combinatorics. Okay, to start off, sequences of series. I know most of y'all know what this is. An arithmetic sequence is a sequence of numbers that have a common difference. In this case, A is the first term, and then each term after that is found by adding D, which is called the common difference, to A. So examples are 1, 2, 3, 4, 5, where A is 1, D is 1, or 4, 2, 0, negative 2, where A is 4, and then D is negative 2. So remember that D can be positive or negative. So it can be an increasing sequence or a decreasing sequence. Okay. So an arithmetic series, like the last word has changed, but it just means that you're summing up the terms in a sequence. So we'll be going over some tricks that will help if you're doing that. And typically, of course, we'll be doing finite arithmetic series, because if we do an infinite series, then it's just going to go on to either positive infinity or negative infinity. Right, so we'll have a finite number of terms. And then here's just comparing. I don't know why I made this. It's just to show like the definitions. Okay, any questions? I'm guessing all of y'all or most of y'all know this. Okay, so the arithmetic series formula too is n times the average of the first and the last terms. Okay, so do I need to stay here? No, I'll stay here for like 10 seconds. And remember that this first and last term, you can actually choose any two terms in the sequence that are like the same distance from the end. So you can choose the second term and the second to last term, or like the third term, the third to last, and so on. You don't have to do the first and the last. And you can prove this by using like the definition of what the arithmetic series is, or what the arithmetic sequence is, by writing it as like A plus D, A plus 2D, and so on. Okay, so here's a quick interlude. My question is, if I'm trying to get good at number sense, why are formulas like these sometimes bad? Like in general, what is the problem with formulas? So tell me in chat, like, what do you think is the problem with always plugging into formulas if I'm trying to get good at number sense? Yeah, so I see a lot of answers that are really similar. One of them is just like, you may not remember what the formula actually is. Hopefully that's not the case, because then you may not be able to do the problem. The other thing is, it kind of like removes gets rid of like the actual number sense in the problem, right? If we're trying to be good at number sense, we're like, look, we don't have to rely on a formula to get the answer. So yeah. Yeah, it's basically, in short, too slow. And I saw a lot of that. Good job. Because typically if we go through a question, we read the question, and then if we use a formula, we have to like in our head mentally map the numbers to the variables in the formula, then do the arithmetic, then get the answer. We want to get rid of this step in number sense. And of course, you could, like, eventually, after enough practice, this step naturally goes away without you having to force it go away. And yeah, I also saw some answers. Some people are saying if you don't know how the formula works, then you should just not use it. Or like, that's okay. Hopefully, we remember how to do the formulas. But you're right. Sometimes like formulas are way too hard to prove. Yeah. All right. I'll go through. So summing up quickly, and here's another thing. All of this text on the slide is only helpful if you can translate it to like a program in your head. So here's what I like to do in my head. First, I practice eyeing the number of terms in a series. So sometimes in problems they give you how many terms there are in a sequence, right? Other times you have to like look at the first and the last, and you know the common difference, then figure it out. But sometimes, most of the time in number sense, actually, they give you a list of numbers. Like they may give you just a list of numbers that looks like this. Of course, they're not circles, but they look like that if you just imagine it that way. And then you want to get to the point where you can look at a list and then see if it's even or odd. And the best case scenario is if you can see how many terms exactly there are. But when there's an odd number of terms and and the list size isn't too long, what I like to do is just take the middle number and then multiply by the number of terms, right? Instead of having to go through this formula, what you're doing essentially is taking the average of the first and last and getting the middle term. So there's really no point to go through the formula. So in this case, to sum up all of these terms, immediately I see there's 7. So 7 times the middle term, that's my answer. Okay, and then with an even number of terms, it's slightly more annoying because you don't have a middle term to work with. But you can either add those two up and then multiply by the number of pairs, or if like both of these are odd, both of these are even, you can take the middle number, then multiply by the total number. So let's just try some problems. I think this should take like 30 seconds to do. Yes, I'm wearing pants. I don't want to prove it though. There are a lot of people. Hi, crispy. Sure. I don't know what that means. Okay, so for the first one, I know there are 7 terms by looking at it really quickly. So 7 times the middle term, 5, 35. So really quick. Second one, 5 terms times middle one, that's 155. And then third one, I'll just take the first and the last. So 16 and 34. And I noticed that these two end in digits that add up to 0. So I probably want to use this. It's probably going to give you a nice number. And in this case, it gives me 50. So I multiply by 2 because there's 2 pairs and then that's 100. There's many ways you could do this. I'm just showing one way. Okay, cool. Any questions? I hope not, because this is just arithmetic so far. Okay. Oops. Okay, special case 1, and you may have heard of this because of the story about Gauss. This is when you're adding up 1, 2, 3, all the way to n. And what is the formula for that? It's on the screen. Okay, so it's n times n plus 1 over 2. N is the number of terms or the last term. And I'll probably talk about this later when we're doing combinatorics, if we get to that. So I really, really recommend memorizing the first around 15 of them. So you want to see a number. Yeah, these are called triangular numbers. Yes. So you have to, like, in your brain, remember what all of these numbers are. So this corresponds to 1, 2, 3, 4, 5, so on. Yeah. Okay. So I need to review this or no? Okay. So the special case number 2 is when you have 1 plus 3 plus 5. So all of the odd numbers up to n. And I didn't have a formula for this because you should just remember it as the number of terms squared. Okay. So the first example is 1 plus 3 plus 5. I can see straight away that there's three terms. So I square 3, and I get 9. Second one, there are 6 terms, 1 through 11. So that's 6 squared, which is 36. And then the last one, I'll just talk about it really quickly. If you only know the first and last term and what the common difference is, you can't be counting out all the terms directly. So you're going to want to do the last term minus the first term divided by the common difference, which is 2, which is 49, then add 1. And that's how you get the number of terms in this sequence. So this sequence right here has 50 terms, so I square that, and I get 2,500. Okay, I see some good questions. I'll talk about it at the end. I'll talk about the homework more at the end. Okay, so let's do these problems. I'll give y'all a minute to do it. Actually, 2 minutes. I think some people are confused. This is number sense class, not calculus, so I don't think we'll be doing L'Hopital's rule. Just a slight confusion there. Okay. So the first one, we should know this: 14 times 15 over 2, 7 times 15. And then this is a number you should memorize. 7 times 15 is 105. Second one, I chose this number on purpose, so we have 1 plus 2 plus 3 all the way to 51. So it's 51 times 52 over 2. And I could either do this by doing 51 times 26. And then in my head, I would do 50 times 26 plus 1 times 26, which is 1300 plus 26, which is 1326. Or I could do what we did last time, 51 times 52 equals, what is it? 2652. And then I divide that by 2. So how did I get this number again? Just a quick recap. I did 2500 plus 3, so I added those together. 3 times 50 plus 1 times 2. So that's how I got 2652. So I'll get rid of that. And then I divided this number by 2 to get 1326. So many ways you can do this again. Number 3, again, numbers are special. I have 1 plus 2 plus 3 all the way to 106. So that's 106 times 107 over 2. In this case, I actually think it's better to multiply the top first instead of doing 53 times 107. So you would be doing 11342 divided by 2, which is 5671. Does that make sense to y'all? Oh, okay, so I'll explain what I did here. I did 6 plus 7 to get 13, then 6 times 7 to get 42. Okay, so number 4, the first 3 were all with common difference 1, so it was 1, 2, 3, all the way to some number n. The other one is 1 plus 3 plus 5, and so on, all the odd numbers up to a certain number. So here I want to be really quick at figuring out how many terms are in the sequence. All right. So I do last minus first divided by 2, and I won't even write this down. So I'll do last minus first, 110, divided by 2, 55, then plus 1. So 56 terms, and I square that. Any questions how I got to 56? That's what you should be doing in your head. And then 56 squared, we've actually done this before. This is 3136. I take 25, add 6 to it, so I get 31. Then I square 6, so I get 36. So that's my answer for number 4. And then finally, okay, 1 plus 3 plus all the way to 19. And this is actually easier than number 4. This has 10 terms. I wanted to show this one because something that may help you, it may save like half a second for you, is that when this number is a 9, the number of terms is either a 10 that like ends with a 0 or a 5. So it like helps you save, helps you double check a bit. That's just something to know. So this has 10 terms in it. Again, this is 19 minus 1 over 2 plus 1, which is 10. So I square 10, and I get 100. Okay. Any questions? Oh, sorry. Yeah, this is, thank you for that. This is 111. minus 1. Okay, cool. Okay, so next we have geometric sequence / series. I just combined it into one because there's really no point of separating it. So in geometric sequence and series, we have the first term A, then each term after that is gotten by multiplying the previous term by r. And we refer to r as the common ratio, a or a1 as the first term, and then n is the number of terms. And n, we only worry about that if there's a finite number of terms. So I will point out that while I was making this, I didn't clarify that the formula here is for a finite geometric sequence. Okay, so let me show you all really quickly, how do we get this formula? So how do we get the formula a times r to the n minus 1 over r minus 1? If my series, is a plus r, a plus r squared. What did I say? Oh, sorry, a plus a times r plus a times r squared, excuse me, all the way to a times r to the n minus 1, then I have n terms. Right? If this was an n instead of an n minus 1, then I would actually have n plus 1 terms. So this has to be an n minus 1. So let me call my sum s. How do I figure out what s is? Tell me in chat, how would you figure out what s is? Let me see how good my erasing skills are. Y'all know on whiteboards, like, do y'all get really pissed when the teacher just like leaves one part unerased or like one line unerased? Okay, I've seen a couple answers. Let me see some more about how you find the sum. I see in the chat something about Q&A, something about related rates. Next class, we'll be talking about everything in number sense tests that you might find. We've been kind of specialized now, but next time we'll be doing like estimation and then units, all that stuff. Okay, so I've seen it a lot of times. What I do is I multiply this number, this entire equation by r. So I get s times r equals ar plus ar squared, and so on up to ar to the n plus ar to the n plus 1. Oh, I made a mistake. Plus ar to the n. So it goes up to ar to the n, and it starts at ar to the first. This one started at ar to the 0, right, because r to the 0 is 1, and then it ended at r to the n minus 1. Okay, so now I have two equations. And ultimately what I'm looking for is s. I want a clean way to represent s. And then I notice that all of these terms are the same, so I'm just going to subtract the second and the first. So I get SR minus s equals, all of these cancel out. So I'm left with a r to the n minus a. And then factoring, I get s equals a times r to the n minus 1, and then all over r minus 1. So are there any questions about how I got this? No? Oh my God. Okay, can we not do that to the Q&A? I'll have to remove anonymous questions. Okay, so the other case I was talking about is the infinite series. So to get an infinite sum, I'll still actually use the formula over here. Recall that my sum was 8 times r to the n minus 1 over r minus 1. Now, what does it mean to be an infinite sequence or an infinite series? That means my n approaches infinity. My n is the number of terms. So an infinite series means that my n approaches infinity. So what happens to this equation when n approaches infinity? So when n gets super, super big, what happens? Well, there's actually two cases. One case is if r is greater than 1. And I'll just assume that r is positive here. So if r is greater than 1, what happens? Okay, I'm very sorry to say this, but like, if the chat continues to be spammed, I'll have to remove you from the meeting. Thank you. And I know it's not any of y'all, it's just a couple of y'all. Yeah, so and this term right here, r to the n minus 1 over r minus 1 gets super big because r to the n approaches infinity. No matter what n is, r to the n is always going to approach infinity if r is greater than 1. And then r minus 1 is a constant, so r to the n minus 1 over r minus 1 also approaches infinity. So at this point, it's undefined. Okay. So we don't worry about when r is greater than 1. We only worry about when r is less than 1. So when r is less than 1, what happens to r to the n? I'll say between 0 and 1. Yeah, it approaches 0. So r to the n approaches 0 because r is between 0 and 1. If I take that to the power of infinity, then I get 0. So that equation would become a to the r n minus 1 over r minus 1 becomes a to the 0 minus 1 over r minus 1, which is a times negative 1 over r minus 1. So I'll write that as a times 1 over 1 minus r. I kind of swapped the bottom side. Okay. So this is the formula for an infinite series. So try it out with these. And I chose them on purpose because I just want y'all to see a pattern. I'm sure many of y'all already know it. And I'll write the formula on this. I'll keep this up. You can also write it as a times 1 minus r. So I'll go through the first one just to show an example. The sum of the first one is a times 1 over 1 minus r. A is the first term, so 1 over 1 minus, and the common ratio is 1/2. Right, because to go from one term to the next, 1 to 1/2, I multiplied it by 1/2, and then same goes for each pair of consecutive numbers. So this becomes 1 over 1/2, which is 2. Yes, okay. So I saw great answers. For number 2, a is still 1, and actually for all of these, a is 1. I just didn't want to complicate things. So a times 1 over 1 minus r, 1 minus 1/3. So that becomes 3/2. 3 is 4/3 if I do it out. And then 4, which is pretty important. This is just n over n minus 1, or I can write it as 1 plus 1 over n minus 1. So why does that work? Well, this is actually a direct plug-in of the formula. My formula was a times 1 over 1 minus r. So a is 1, r is 1 over n. Oh, my bad. So this becomes 1 over n minus 1 over n. So n over n minus 1. All right, any questions? I get weird messages on this computer. I really don't know what's going on. I don't think there's a virus though. That'd be really sad. Okay, any questions? All right. So try these out, and then I'll give y'all, I guess, 30 seconds to do this. All right, 10. Okay. So how would y'all do number 1? I'm just wondering. How did y'all do this? Actually, what I'm hoping is that you didn't use the formula. Okay, good. I'm sure y'all are good with that. So this was, can I add? Yeah, it's 40. The second one, and this is for all powers of 2. If you start at a number and then go up to a certain power, you take the last number and then multiply by 2. So basically you're getting the next power of 2, which is 2048. Then subtract whatever the first term is. So in this case, that's 1. So I get 2047. So I'll do that for the third one. The next power of 2 after 256 is 512. So I subtract the first term and I get 510. And then the last one, again, I don't want to be using a common ratio of 4/3. I could, but in number sense, it would be better to like just add it than check for, rather than, or as opposed to like checking for a common ratio then using the formula. So adding it, you should get 175. Okay. Any questions so far? I know this is a review for a lot of y'all, but I'm just hoping that either if you haven't seen it before, you know it, and if you have seen it before, you get really fast at it. Okay, so we have other special sequences. Have y'all seen this before? I'm guessing you have. So they're actually a bit hard to memorize, at least like the ones, the first one. So the first one is 1 squared plus 2 squared plus 3 squared all the way to plus n squared. And that equals n times n plus 1 times 2n plus 1 over 6. And you can prove that this number is always an integer. That's not too hard to prove. For the next one, 1 cubed plus 2 cubed plus 3 cubed all the way to n cubed equals n squared times n plus 1 squared over 4. And does anyone know why, or why you might have seen this number before, or this formula before? Why does this look familiar? And I'm talking about the second one. Yeah, it was our formula from before, n times n plus 1 over 2, but everything is squared. Okay, so now we're actually going to do something a bit different from what we normally do. How do y'all think we should prove this statement? So we're actually going to prove this first statement, and if we have time, the other one. So how do you think we would prove this statement? So I guess it's a new topic for a lot of y'all. We'll prove this using something called induction. I saw some of y'all know what induction is. Okay, so induction works when you're proving a statement about all numbers and all of these numbers are, I'll just say integers. So I'm proving a statement, this one specifically on the left, about all natural numbers n. So all numbers n, this statement should work for it. So my bottom case is n equals 1. So if n is 1, then 1 squared equals 1 times 1 plus 1 times 2 times 1 plus 1 over 6. I'll verify this. Is this true? Yes, it is true. It does work. Okay. Now, here's how you write up an induction proof. In induction, what we're doing is kind of like going up a ladder, and this is an infinite ladder. So I don't know. I don't really have like a good setting for this. I'll just say we're in space. All right, so we're just climbing up an infinite ladder. We start at rung 1. This is case n equals 1. So this is our first one. And we have to prove that we can, in the first place, step on this. So can we step on this? Is n equals 1 true? And yes, I just showed that when n is 1, this formula does in fact work. So what induction does is, now if I can get to any certain rung, so let's say this one, is it possible for me to prove that the next one is also true? Okay, so if I can prove that if I can get to this one, then I can get to this one. Then I can start from 1, and I know I can get to 2. From 2, I can get to 3, and so on. And basically, I prove this for all numbers. Okay, so I'll write it up now using induction. And there are 2 main steps in the proof I just outlined. The first is called the base case. And the base case is the smallest example that has to work. In this case, my base case occurs when n equals 1. So when n is 1, I just have to verify that 1 squared equals 1 times 1 plus 1. So this is indeed true. And then next, my inductive, I guess, hypothesis. So my inductive hypothesis is, I'm assuming I can reach rung k. So I'm assuming that when n is a certain number k, it works. So in terms of this problem, what does that mean? I'm assuming that this formula holds for a specific number k. So this isn't any number k, but I'm assuming that it works for some specific k. Now, what do I want to show? I want to show, I'll maximize this now. Okay, I'm very bad at using MS Paint. Okay, I want to show that when n equals k plus 1, that statement also works. So this also translates to showing that 1 squared plus 2 squared plus all the way to k plus 1 squared equals k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 over 6. I want to show that this statement is true. Okay, so see if you can go from this statement over here and then get to this one. So remember that the equation, oh my God, the equation underlined by red, are you serious? It happened again, okay. The red underlined equation is the one that we're assuming is true. So what would you do to get to this equation? Well, if I want to go from something that's true to something that isn't necessarily true, then I always want to start off at the statement I know for sure is true. So from this one, I'll go to an intermediate step. So the difference between this left side and that left side is that this one has an extra k plus 1 squared. So I'm going to add k plus 1 squared to both sides of this equation. I have that, and then the right side plus k plus 1 squared. And then if I expand this, do a bunch of arithmetic, I actually do in fact get this. So if I do a bunch of ugly math right here, then I get to this final statement. And recall that I still know that this statement is true. This is still all from my original red statement. And this is in fact exactly what I'm trying to prove here. Okay, so were there any questions about how induction works? Like the logic behind it or a certain step in here? Well, okay, no questions. That's okay. So I was gonna actually save the proof for the next one for y'all to do, but I don't think we have time for that. We only have 8 minutes left. I'm gonna go really quickly into something maybe new. So before that, try out these 4 problems. Are these the same? Oh no, okay. I guess I'll do what I was going to. So first I'll answer the questions in the chat. I saw one question was like, the formula for geometric sequences doesn't work. Can you explain that again? Okay, so this was the formula for geometric sequences. And the proof for that, if you recall, was S equals A plus AR and so on. And then I subtracted those, and then I divided both sides by R minus 1. Okay. Any other questions? All right. So I don't know why it's not showing up here, but I also wanted to talk about something we did last time. So last time we talked about divisors and how to do the divisibility rules fast. So next time, what we'll be talking about is number of factors. So everything about factors, the number of them, the sum of them, product of them. We'll also be talking about estimation. And with this subject of estimation, let me go to the homework and then talk briefly about that. We'll be talking about estimation and then other random things you'll find in number sense tests. So if you haven't been doing the homework, which is actually a lot of you, that's okay. But let me explain like what I'm expecting from it. Okay, so here it is. So I noticed that a lot of y'all aren't doing the number sense test or just doing one section. So to get credit, just do one of those sections. But I'd really appreciate seeing both of those sections being done. So about number sense scoring, you'll notice that in most number sense tests, you have 80 questions. And most people give you 10 minutes to do it. All right, so 10 minutes, 80 questions, that's 7.5 seconds per question. That's why I'm like giving you 1 minute or half a minute to do each question. I really want y'all to get to the point where you can like do all of this. So the grading works by giving you +5 for every correct answer, -4 for every incorrect answer. And that includes all the skip problems you did before the last question that you answered. Oh, my bad. So let's say I answered the first 14 questions, which is okay if this is like my first time doing it. So let's say the last question I answered was number 14 and I skipped number 12. So skipping number 12 in this case would count as, it would actually count as an incorrect answer, so -4. Besides that, I saw another question in the chat was, what is this asterisk? It means that it's an estimation question. So every 10 questions, there's an estimation question. So 10, 20, 30, all the way to 80, 8 of them. And you just have to get within 5% of the correct answer. So in this case, like number 30, there's no way you're doing this in your head in like 30 seconds. So you just have to estimate what that value is. All right, let me see, is Rotren here? Rotren's not here yet. Do y'all have any other questions about Kid Teach Kid or homework? Homework, you can actually do it at any time. I think we'll stop counting homework and any other points on the last day of class. What is a boast poem? A boast, it was something for school. I really didn't like it. The recording will come out. I'm actually not sure. You'll have to ask Rich about that. I'm pretty sure they come out actually like the day after class. And these, I don't want to talk about what those are. Anyways, is Rochan here now? Okay, I'll mute myself, and then when Rochan comes, I'll turn it over to him. Anyways, thank you so much for coming. If you just came, remember that we have a math contest going on. You can get to it by Kid Teach Kid and then go to math contest. Besides that, have a nice day, y'all.